Okay, so we're just about to start the second talk of the morning session. We will have Carlo let me get the name right. It's always embarrassing when you get the speaker's name wrong. Carlo Marinelli will be talking on functional inequalities, and there will be a number of lectures over the following few days. He's based at UCL, and I will now turn the podium over to Carlo.
Excuse me, can I just make one remark? Ian is using the wrong, you probably used the wrong version that I sent previously. So the correct title of the talk is Analytic Inequalities.
All right, there we are. I stand corrected.
Yes, no, it's correct. So, sorry.
So if you share your screen, Carlo.
Hi, Ian. Have you recorded the meeting?
Yeah, it's recording.
Okay.
Carlo?
I'm here. Can you hear me?
Yes, and yeah, there we are.
Actually, my camera is already my video, so I don't have a video to share. As soon as I talk, I suppose my video should become visible.
Okay, so if everybody moves to the speaker,
yeah,
and the screen, we should all be okay.
Exactly. That's what I'm going to do.
Okay.
Maybe I could also add, in principle, there is a possibility in Zoom to pin somebody. So you may pin Carlo Marinelli, and in that case, even if Carlo is not speaking, you can still always see his screen. So this is one more option, so that Carlo doesn't need necessarily to speak all the time, so that you see him constantly. Sorry about that.
Yeah. The pin is the best solution. Okay, so let me start then. Please let me know if there are any issues. As you see, I'm using old technology. So I will actually talk about very elementary analytic inequalities, but that are used actually in, I would say, most areas of mathematics. The content of the lectures are indeed very simple, and we will mostly look at inequalities for sequences or for elementary integral. So someone says that there is a problem with pinning my page, but I don't know whether it is a common problem because I can see everything by pinning myself. So hopefully everything is all right. So we will look at inequalities. Okay, so everyone says that. All right. So we will look at inequalities mostly for series. So for instance, we will try to look at, let's say the title, I will just say inequalities. And I will just give some examples of things that we are going to look at. So we are trying to understand whether we have an inequality of the type sum of ai to the power p 1 over p. And then here, for the time being, we just look at finite sequences, whether we can bound it with an analogous sequence finite sum with a different exponent, again on the same index set, of course. Oh, by the way, do you see everything reverse, or is it just me?
Everything's fine for us.
Okay, very good. So it's reverse for me, but good. And so we are going to prove that, in fact, this is the case whenever we have that 0 is less than q is less than p. Most of the time, just I use this example to give some conventions and notation. Most of the time, we will only look at cases where ai are larger or equal than 0. And later on, we will actually introduce also some cases where exponents can be negative. So we will actually even restrict to the case where all AIs are strictly positive. So a common let's say notation that we're going to use often. So I'm not assuming any particular knowledge on sequence spaces or anything like that from even from basic functional analysis, because I assume that not everyone in the audience does. But so we will use some notation as the following one. So this this quantity here will be denoted as A with these two bars LP, and later on we will actually see more detail why this notation is meaningful and what characteristics it has. For the time being, I just wanted to make an observation that an idea that we are often going to use and to look at is homogeneity. So in particular, look that both sides of this inequality are homogeneous of order 1. So I briefly remember what homogeneity is, just for the sake of completeness. Maybe I give a relatively general definition. Because it will turn out to be possibly useful for future developments. So suppose that we have E and F, two vector spaces on the same field K. Most of the time for us, the field K will be R. Very few times it will be C. Sometimes we will say something about even more general situations, but there is no problem if we are not familiar with even basic notion of algebra. Just think that this is a standard vector space on R, and then we take a map from E to F, and we say that this is homogeneous of degree alpha if the following is true, that f of lambda x is equal to lambda to the alpha f of x for all x in E and for all lambda in K. And if we have that K is a subfield of R, then we have a notion of positive homogeneity. So positive homogeneity will means that f of lambda x is equal to lambda alpha f of x, again for all x in E, but now we require for all lambda that are positive. You see that we need that K is a subfield of R in order to have a notion of order. So sometimes people also ask lambda larger or equal than 0 rather than lambda 0 only, but okay, this is not really important for us. So why do we, where are we going to use this? What is the idea that we're going to exploit quite often? Well, you see that if you have that the left-hand side and the right-hand side of an inequality are homogeneous functions of the same variable, in this case of the variable here is the vector A in Rn, so a sequence with n numbers, of course, is an element of Rn. This can be rescaled because you see that if we multiply lambda, this inequality will be true if and only if we multiply by a certain positive lambda both sides of the inequality. So we could, for instance, take a lambda such that the right-hand side of this inequality is equal to 1 or equal to any value that that we prefer. So how is this going to help in this specific case? So I just give an example of how we use homogeneity. So this this example, so let's see how it works in this example. We want to prove that an equivalent to that statement is that if A LQ is equal to 1, then we want to prove that A LP is less or equal to 1. Okay, so this is what we want to prove, and the two statements are completely equivalent. Now, I claim that proving this is very easy, and why? Well, because let's look what we have. We have that AI to the power P, 1 over P, this can be written as the sum of AI to the power Q to the power P over Q, and then to the power 1 over P. Well, but what can we say about this? Well, look, since we assume that P is larger than Q, P larger than Q, then we have that, we know that this sum is equal to 1, so each element AI will be less than 1. So since PQ is larger than 1, this element will still be smaller. So this is less or equal than the sum of AI to the power Q and to the power 1 over P. Well, but we already know that this is equal to 1, so this is 1. Okay, so the proof is very quick just by using this normalization idea. And so as an exercise, I suggest you to try to prove the inequality without normalization. So I call normalization, or in the sense of exploiting homogeneity. So you will see that the proof is not at all that trivial, as a matter of fact. And in the end, the most natural proof, actually, which, by the way, requires a little bit of thinking, is exactly to resort to an idea which is equivalent to normalizing. So try to do that, and you will see that it is not, it is doable, but not really trivial, as it is in this case. Homogeneity is a little bit tricky in some cases, tricky in the sense that one has to be careful not to fall into rather common mistakes. So let me give an example of other inequalities that we're going to look at, and they are very good examples to discuss some types of homogeneity that we have. So for instance, we are going to prove this very famous inequality due to Cauchy, which says that we can bound this products, the sum of the products, by the square roots of the sum of the squares. So if we allow ourselves to introduce a further notation, so again, here we look at finite series. Okay, as a matter of fact, we will see that once we establish the result for the finite series, the result carries over to infinite series as well. But let us allow ourselves the introduction of a further bit of notation. So this is, we use this angle brackets like this to denote, as you notice, this is nothing else than the usual scalar product in Rn for the time being. Okay, and here we use the notation that we've used before. So this is just in order to keep things simple, if you like, but simple in the notational sense. Okay, so notice that here we have actually even more homogeneity than before, because if we look at the left-hand side and the right-hand side, we notice that the left-hand side is homogeneous in the variable A, in the variable B, and jointly in the two variables. Someone is asking whether I can make it larger, but unfortunately there is a hardware limit of the camera. I cannot make it larger. I mean, the only way I have to make it larger is to write on a smaller piece of paper, but I don't know, I'm really sorry, but I'm not sure I can do much. So I was saying that here, if we look at the left-hand side and the right-hand side as functions of A and B, we have separate homogeneity of order 1 and joint homogeneity of order 2. Okay, so in this case, this is very strong type of homogeneity, because this suggests that in order to prove this inequality, we may normalize both A and B. So we may assume that both this quantity, this is double brackets of B L2 and double brackets of A L2 are equal to 1. So these sums are equal to 1, or just one of them is equal to 1, or whatever other normalization we believe it could be useful. So let us look now at another inequality that does not satisfy this very strong homogeneity condition, so that one has to be very careful about. And this other inequality, we will see all of them later. So these are this is inequality due to Minkowski. Sorry, this is cursive p, but maybe I write it like this. So this is less or equal than the sum of ai to the power p 1 over p plus the sum of bi to the power p 1 over p. So now this inequality is again an inequality between two sequences, but this inequality is not separately homogeneous, it is just jointly homogeneous. Okay, so if you multiply AB by lambda, then you have that lambda appears in both on both sides, but you cannot just multiply A by lambda because you won't have an identity. Okay, so one has to be very careful, because one, by looking at this, would let's say jump on the conclusion, okay, let us fix this equal to 1, this equal to 1. Well, you cannot do this. Okay, you may fix the sum to 2 if you like, but you cannot fix either this part or this part to be equal to whatever you like independently of each other. Okay, this is not possible. So I gave an example of two inequalities where one has a very strong normalization, well, homogeneity, which induces a lot of normalization. This one has some normalization, but jointly only, not separately. Okay. Okay, so now that we have introduced a little bit of terminology, let me also briefly remember an informal old suggestion by two famous English mathematicians, together with a Polish one, Hardy, Littlewood, and Polya, who suggested in their very famous book to always watch out for homogeneity in the symbol of summation. Okay, so this is mathematically nonsense, of course, right? But this is a very useful trick to check whether an inequality may be suitable. So someone, okay, there is a question which I will answer in a second. The observation by Hardy, Littlewood, and Polya is that if you have an inequality which is formally homogeneous in the symbol sigma of summation, so you treat sigma as a letter, if the inequality is homogeneous in that symbol, then this inequality most likely is true for averages, not just for sums, and also for integrals. Okay, so this is just something that I suggest to keep in mind, and the question is whether one can use joint homogeneity to fix the sum of the ai to 1. Certainly you can, but I'm saying that you cannot fix whatever value you want for the sum of the ai and the sum of the bi's separately. Okay, this is not something that you can do. And the reason is that the two sides of this inequality are homogeneous in the couple AB, not as a function of A and as a function of B. Okay, so let us move to the first character of our course, which is the Cauchy inequality, and we are going to give several proofs of it. So let us repeat what it is actually, the Cauchy's inequality. And it is just this. So let us take A, B, Rn plus, so elements of Rn with positive elements. So I use let's say the non-Anglo-Saxon terminology for positive and negative. Positive for me means non-negative. If I want to say larger than 0, I will say strictly positive. Okay, so I really don't like non-positive, non-negative, and all that. I prefer positive statement to negative statements. So I apologize if you are used to a different terminology. So we are going to show that this identity this inequality, sorry, is true. And the fun of working with inequalities is in part that there are very many questions that arise naturally, and I would like to do exactly this exercise with you. So to show you where questions arise, what kind of questions you may look at, whether in general they are difficult or not. So in some cases they will, in some cases they will not. And also we will give most of the time several proofs of the same facts. Okay, so here I just wrote the concise form of the inequality. And whenever you see an inequality, the first thing that you should, the first things that one could rather than should ask is whether can we also identify if there are cases of equality? And another typical question is, are the constants involved sharp? So clearly, if I show that there is an equality, then the constant involved is indeed sharp. So can we say something about the case of equality here? In fact, we can say something, but I say immediately what it is. So with equality, but we will prove it in the second proof, not in the first. With equality, if A, B are proportional. Proportional, or if you prefer the better language of linear algebra in Rn, this just means that A and B are linearly dependent. Of course, it is exactly the same. Okay, so let us see how we could prove this inequality. Maybe a very short comment before. This inequality extends immediately also to A and B. So if you take A and B in Cn, the inequality is so find correct version. And this I would leave it with you, but I simply remind that if you take the modulus on the left-hand side, then you have finite sum of complex numbers. You just take the modulus inside. Then the modulus of the product is the modulus of the both terms, and then you're back to this case. Okay. So this is the reason why I said, an example of the reason why I said, with an instance of the situation that I described before, where I say that treating positive sequences is for our simple purposes enough. So whenever you have a problem indexed by the natural numbers, a natural idea is to try whether you can easily understand what happens with low values of n. So you see clearly that if n is equal to 1, this is a total triviality. There is absolutely nothing to discuss, right? So let us have a look at the case n equal to 2, and let's see what we have. Well, we have a1b1 plus a2b2. And so instead of looking at this case with with the square roots on the right hand side, we'll just take the square, and we know that if we take the square on both sides, the two inequalities will be equivalent, because we are looking only at inequalities between positive quantities. So that's why I first look at this square. Okay, and this, we know it is trivial. This is a1 square b1 square plus a2 square b2 square plus twice a1 b1 a2 b2. And we would like to compare it with the right hand side, which is a1 plus a2 square, b1 plus b2 square. And here what we have? Well, we have just the products of all possible combination with the squares. So we will have a1 square b1 square plus sorry, I made a mistake. Of course, the square is inside, otherwise it makes no sense. a1 then a1 square b2 square plus a2 square b1 square plus a2 square b2 square. Okay, now let us compare this and this. Then we have that this term and this term are the same, this term and this term are the same. Okay, so we are left to having to prove that this term is less or equal than this term. Okay, so we would like to prove that this inequality is true. Well, is this correct? Well, you can convince yourself that by maybe just doing a little bit of regrouping by using just the commutative property. This is nothing else than x minus y square larger or equal than 0. Okay, so because we know that this means that very important inequality actually, that xy is less or equal than 1/2 x squared plus 1/2 y squared. Okay, or in other terms, that 2xy is less or equal xy plus y squared And you see that in this case we simply have a1 b2 b1 a2. Okay, so then we see that the case n equal to 2 is slightly less trivial, but still very simple. So we have indeed that Cauchy's inequality is true trivially for the case n equal 1, and we just verified for the case n equal 2. So at this point, it is very natural to say, well, let us try immediately then the passage from the case n minus 1 to the case n. So this will be the general induction step. If this is true, then we have established the inequality. Okay, so let's see whether we can do this. So we write the following. We write sum ai bi from I equal 1 to n is equal to the sum ai bi until n minus 1 plus an bn. And now what do we do? Well, now using the induction step, we use the inequality on this term, correct? And therefore we have that this is less or equal to the sum of ai squared up to n minus 1 to the power 1/2, then sum bi squared up to n minus 1 to the power 1/2 plus an bn. So I have used the case n minus 1, which we assume to hold because we are doing the induction step, okay, on this term, and we have this inequality. Now, what is the very natural thing to do? Well, I use again the Cauchy inequality for the case n equal to 2, where I give a name to this guy, I call it alpha, and I call this beta. Okay, so I apply the inequality, I apply it here, and I will have that this is alpha squared plus, so let us write it completely, alpha squared plus an squared 1/2, beta squared plus bn squared 1/2. Well, but what is alpha squared plus an squared? This is nothing else than the sum of ai squared until n. Right? And the same is true for the other part. So we have sum of bi squared until n to the power 1/2. And so we have concluded the induction step, and the proof of the Cauchy inequality is complete. I suggest you to check whether you can prove the statement about equality. So I claim that you have equality if and only if A and B are proportional, or if and only if A are linearly dependent. So you will see that you can do it, but it's a little bit, let's say, inconvenient. We will now talk about another idea, which actually will give a slightly more convenient way to proving also the case of equality at the price of slightly more algebra, but still getting, let's say, in a sense, more complete result in the following sense, that another very common question that people ask when looking at inequalities is whether we can quantify the difference between the two sides of the inequality. So In particular, what did we just prove? Well, in the step n equal to 2 of the Cauchy inequality, we have proved the following. We have proved that a1 squared plus a2 squared multiplied by b1 squared plus b2 squared minus a1 b1 plus a2 b2 squared. So we actually found an explicit expression for the difference. If you look at the computation that we just did, you will see that what we found is exactly the following, that this is a1 b2 minus a2 b1 squared, which is obviously larger or equal than 0. So an alternative proof of Cauchy's inequality goes through an extension of this identity, and an extension to this identity to arbitrary number of summands n goes under the name of Lagrange identity. So, and we have the following lemma. So Lagrange identity, which says the following. It says that if we generalize this, so if we write ai square and we multiply this by bi square, so the sum is finite. I don't write all the time I equal 1 to n. If I don't write that, the sum is finite and up to n. It's our standard convention. And then we do minus the sum of ai bi square. Then we will have the following thing. We'll have that we have the sum extended over all indices I and j both going from 1 to n, but we only do the sum when I is less than j, of ai bj minus aj bi square. So you see immediately that this object is certainly larger or equal than 0. So the Lagrange identity immediately implies the Cauchy's inequality. Not only it tells you exactly what the difference is, and also by looking at these terms, it will tell you immediately that you have identity in the Cauchy inequality if and only if this sum is equal to 0. But that happens if and only if each of the summands is equal to 0. Therefore, if and only if, so let's say, before I prove it, let's say corollary, 1, Cauchy is true. Second corollary, we have equal in Cauchy if and only if we have ai bj equal aj bi for all I different than j. Okay, so this corollary stated like this is obvious. If we try to prove that this is equivalent to, so we would like to prove, so this is obvious. But is it obvious that this implies that A and B are linearly dependent? Of course, we see that this implication is trivial. So this implication is trivial because this will mean that AI is equal to lambda bi, right? So you replace lambda bi here and you replace here lambda bj, you end up with lambda bi bj equal lambda bi bj, which is obviously true. Okay, but however, if we want to go from this side to this side, it is not entirely trivial, right? Because it is trivial if you assume that all of these objects are not 0. Then you just write ai over aj, ai over bi is equal to aj over bj. Then everything is fine in that case. Okay, or yeah. There is a problem, however, if you start assuming, well, but why do I have to take them all different from 0? So we will return to this case later, because if you fix some of them, if you have one of them equal to 0, then you start running into minor trouble, but you can get out of it. Before we do that, let us give a proof of the Lagrange identity. This is I think, a simple but useful exercise in manipulating finite sums. So let us see. So proof of the lemma. So we start with the following identities. So the first is that we look at this quantity. So we have that the sum of ai square and the product bi square. This can certainly be written as the sum of ai square bj square. Now the sum is extended really to all I and j, not a different than j, all of them. Okay. Okay, so first we write this in this form, and then we look at this with this other term. So what about that term? So well, that term ai bi square, and this we use something that we remember from our high school years, maybe even before that. So we take sum of the squares and double sum of the or sum of the cross products. Okay, so we just write it as sum of ai square bi square, and then we should write. We have two options to write this. Either we write sum of ai bi aj bj for all I different than j, or we can order it by symmetry, and so we use symmetry. We write plus twice I less than j, and we write ai bi aj bj. Okay, this is exactly the same thing, just by using commutativity and reordering. Okay. Very good. Okay, so let us now. So now the idea. What is the idea? Well, simply you see that I have this term here, and I want to compare the two and play around with them. Okay, so let's see what we get. Yes. Notice that the important difference here, maybe I should highlight it here, is that these two sums are not the same. Notice that we have an index j here and we have I here. Okay, so this is the point where we have to pay attention. So, and this is the next step that we are going to take. So then we have the following, so that the sum of ai square sum bi square minus sum ai bi square. This will be equal. So to so notice what we have. So here we take all the I and j. Okay. So in particular, also the case where I is equal to j, and here we take only the case where I is equal to j. Okay, so what are we left with? If we take this minus this, we're going to be left with this sum when I is not equal to j, because the equal case is all eliminated. Okay, we subtract it. So we write it then as sum of I square bj square when I is not j, and minus 2, and the sum that we had before, which was ai bi aj bj, and again I not equal to j. Okay. Sorry, this is I less than j. I apologize. Okay, now we have the problem that we have this I different, I less. So we would like to find a way to compare them. And here we have a very let's say, I don't like the word trick, but it is just, let's say, an observation. It is a simple observation that we can certainly split the sum in two parts when I is less than j and when I is larger than j. So first we split like this and we write ai square bj square, and then we look at the other part. So we have ai square bj square, but here we take a larger than j, and the second part we simply copy it. So we have ai bi aj bj and I less than j. Okay, so again we would like to compare only one sum in order to be able to do things in a simple way. So this is just an interpretation. What is the interpretation of this term here? That we are summing, we are taking these sums over all indices where the index of A is larger than the index of J. But if we relabel, this thing is nothing else than plus the sum of I less than J, A J square, B I square. Okay, so now we are happy because we can, let's say in a slightly incorrect way, we can collect the summation symbol, right? In other words, we can put everything under the same summation sign. What do we get if we get everything under the same summation sign? Well, we have AI BJ square, AJ BI square, and look, AI BJ, AI BJ, AJ, BI. So this is nothing else than the sum of AI BJ minus AJ BI, I less than J, and this is square. Okay, and the proof is completed. So we just manipulated a little bit and we completed the proof. So let me give a very short remark that there is a formula. Maybe this is something that you could look for yourself. I just give this remark that the Lagrange formula, the Lagrange identity, is a special case of, so it is a special case of the so-called Binet-Cauchy identity of algebra, and have a look at that and convince yourself that the Binet-Cauchy identity holds for sequences that take values in any commutative ring. So let's say holds in any commutative ring So in particular, this means that the Cauchy inequality is meaningful and does hold in any commutative ring. You don't need the real numbers. You don't need reals. You don't need Cauchy. You don't need complex. Any commutative ring will do. So of course, now then, of course, a natural question again appear that we are not going to touch upon. Is there something similar also if we remove the commutativity assumption? You know that you see that we strongly use the commutativity assumption. So it is very hard to come up with something that does not use the commutativity hypothesis. There is something in some very special cases, but we are not going to touch upon this. I mention this because this is just the typical way that one proceeds when one asks questions when is discovering things. We pretend we are discovering things now. So even if we are just at least what I'm doing is exposing things that have a rather long history. But I hope that for many or most of you, this is a useful discovery process. Okay, so now let us briefly look at the fact of establishing that the Lagrange identity, in fact, gives also the case, gives also a proof of the fact that there is identity if and only if A and B are linearly dependent. We already proved that linear dependence does imply that the summands in the rest in the Lagrange identity are zero, so this implies that there is identity. But what about the other case? So we said that there is a problem if we assume, we would like to, so let me number this is number 6. We would like to say that this equal to 0 implies that the vectors AI, the vector I and the vector B are linearly dependent, which is not clear unless we assume that all of this, so this is for all I less than different than J, unless we assume that all the quantities involved are not zero. This is not trivial. Okay, so, but first we proceed in another way. So let us remember, this condition is equivalent to having equality in the Cauchy inequality. So, but let us suppose that any element of this is 0. So for convenience, let us assume that AI is equal to 0. So let's look at this. So AI, BI, or maybe let me say AJ, so it is easier just for labeling purposes. So if we look at the sum of AI, BI from I going from 1 to n, of course, since AJ is equal to 0, we can just forget about it, right? So we can just say that this is AI, BI if we take I, not J. But if we take I, not J, we know that we have established the Cauchy inequality. We have established always. Okay, so we are just so we would have that this is less or equal than AI squared. But now in this case, right, and sum of BI squared 1/2 in the case I, not J. So what happens now? Well, look, if we have AJ equal to 0, I claim that if we have equality in the Cauchy inequality, we must have BJ equal to 0. Why? Well, because suppose that it is not the case, that the BJ is not equal to 0. Then this quantity is strictly dominated by sum of AI squared on the whole I. We don't care because AI is equal to AJ is equal to 0, so these and these are the same, but this quantity is strictly less than this quantity, BI squared 1/2, where now if I don't write anything, the sum is extended also to I equal to J. So here we have strict equality, but this strict equality contradicts the hypothesis of having equality in the Cauchy inequality. Okay, so what have we proved? We have proved that if we have equality in the Cauchy inequality, this means that AJ equals 0 implies BJ equals 0. So it means that if we have an element, a vector A, B, of which we are doing this trick, then we will have that if a component of the vector A is equal to 0, the same component of vector B must be equal to 0. Why is this helpful? Well, because it means that we can, once we make this observation, then it means that we can restrict the sum, in fact, to those elements I, such that AI and now we can say and BI are not equal to 0. But then we are back to the case that we know. Because since we know that all of these guys will be not 0, then we have already argued that this identity will in fact imply that A and B are proportional. Okay? Because from this, we simply write that AI, BI is equal to AJ, BJ. Okay? Which is exactly the same as saying that there exists a constant. So this is equivalent to saying that there exists a constant K such that A is equal to KB as vectors in Rn. Okay, so then we have established the whole thing, and I either went much slower than I thought, or I prepared too much material for one lesson, so it depends how we want to see it. So I was told that I should left 10 minutes for questions. So I have another couple of minutes that I will use just to introduce something, and then we will move. I will stop there. So I will just introduce some notation that we're going to use for next time. If this is well known to you, very good. If not, just learn or try to remember for next time. So our next step that I wanted to do today, but it won't be possible, will be to discuss yet another proof of the Cauchy inequality, which is due to Schwarz. And this is the reason why actually this inequality is wrongly called the Cauchy-Schwarz inequality, because in fact, There was another guy from Russia, Bunyakovsky, who proved it much earlier than Schwarz, but for an historical accident, this inequality is now called as the Cauchy-Schwarz inequality, although many Russian textbooks do call it the Cauchy-Bunyakovsky, sometimes Cauchy-Bunyakovsky-Schwarz inequality. Anyway, in the setting that we want to look at, we will look at the following situation where V is a vector space. V is a vector space, now not on a general field, but on R. Although it could be on C, but not under exactly the same hypothesis. And on this vector space, we endow the vector space with a so-called inner product. What is an inner product? Well, an inner product is a map or a form. So a map, when usually in mathematics there are many names. So when you have a map which takes values in R, very often this map is called form. Okay, well, not necessarily in R, but on the field of scalars. So what does this? So we take two vectors of two vectors of V, A and B, and this will be mapped into this square bracket AB. Now you will wonder, isn't this in conflict with the notation that you have already introduced? And the answer is no. So it is just using computer science terminology. This is an overload of the previous notation in the sense that it is in the special case of the previous case. It is perfectly compatible with that, and I will say when. It is actually trivial. Okay, what are the properties of this map, of this inner product? So how is defined? So this needs to be symmetric. Symmetric means that AB is equal BA. Okay, then it needs to be positive definite. Positive definite means that AA is larger or equal than 0. But actually, I actually require strictly positive definite in the sense that AA is larger or equal than 0, but equal to 0 if and only if A is 0. Okay? So this is what I call strictly positive definite form. And the last thing is that it must be bilinear or bilinear, depending on how you prefer to pronounce it. I prefer B. So bilinear means that the function A to AB is linear and the function B to AB is linear. Okay, so I suppose that in your previous course in linear algebra, you have seen the definition of symmetric and bilinear form, so I don't think I need to go very much in detail about this. The important fact is that we will assume that AA is larger or equal than 0 with AA equals 0 if and only if A is 0. Okay, so this is very important. So if you assume only that the form is positive definite, not strictly positive definite, this is also called a semi-inner product. So we will prove the following fact, and then I stop, that we can have the Cauchy inequality on any vector space endowed with a semi-inner product. Okay? To avoid too much generalization, we will just stick to the case of inner product. And I will leave to you to check that the Cauchy inequality is still true if you only assume that the form, square brackets, angle brackets, is only positive definite, not strictly positive definite. So, okay, I went slightly overboard, but since I know that there is a break after my lecture, I took advantage of that. So sorry for the delay. So now, if there are any questions, I'd be happy to answer them.